Hello everyone. In this course we are going to talk about the moment of inertia. The moment of inertia, it falls into two categories. The first category is the area moment of inertia, or sometimes called second moment of area. This term is used for determining the stresses due to shear and moment and torsion acting on a given section. This is the moment of inertia under this category is dealing with the statics problems and how to solve these static problems by use of the moment of inertia. The second category is about the mass moment of inertia. This represents the resistance of a body to angular acceleration due to torque, and this topic is very important in the study of dynamics. In this course we are going to talk about the area moment of inertia, and for the mass moment of inertia it will be later on discussed. How we are going to perform our estimation for the second moment of inertia. We are going to draw the x and y axes, and for example, if we have an area in this shape, we are going to introduce strip, and we call that strip area is dA. If we are going to evaluate the inertia about the x-axis, we need to know the y dimension, or the vertical or normal distance to the x-axis, and we are going to say that the inertia moment of inertia about x-axis is equal to the integration of dA multiplied by y squared, while for the moment of inertia about the y-axis, as we can see, is equal to the integration of dA multiplied by x squared, where the x is the normal distance to the y-axis. In this regard we are going to use vertical strip. This strip area we call it dA. The integration itself, the integration symbol is the same like the summation of individual areas, and in that regard each area will be multiplied by its x component. But this symbol integration, it means that we are going to move this strip multiplication by x squared starting from one point ending to another point. Next item will be the product of inertia. Suppose we have big area like this, where the area we call it capital A, like that. We will introduce only small strip of area equal to dA. From that strip we are going to estimate the CG distance for both the x and y coordinates. The x is the normal horizontal distance perpendicular to the y-axis, while the y is the vertical normal distance perpendicular to the x-axis. The expression for Ixy equal to the integration of dA multiplied by x by y for that strip, which this is equal to the summation of, for example, a1 x1 y1 plus a2 x2 y2, etc., where I equal to 1 until I equal to n. At the end, instead of performing this task, we are going to introduce only one small strip, and we start from our start point, integration from our start until our end. What are the steps to estimate the moment of inertia? First, we draw the element to know what is the shape of that element, either rectangle, triangle, trapezoidal, etc. Number two, form an expression for the dA by introducing the strip, and we will find out this is a horizontal strip or vertical strip. What is the relation between x and y? This is the third step. Write the expression for both x and y and making interrelation between them. We need y if we are going to estimate the inertia at x-axis, and we need the x distance if we are going to calculate the iy, and of course we need both x and y if we are going to estimate the product moment of inertia. Number 4, we are going to set the limit starting moving of the strip. What point will start until what point it will end, and some cases, especially in the triangle, we are taking the integration by 2 steps, as we are going to see. Number 5, make the integration. We estimate the integration values, and then at the end we are going to evaluate the moment of inertia. There is a very important theory which is called parallel axis theory, and we are going to prove it for Ix. Suppose we have two intersecting axes, namely x and y, and this is the area we are going to estimate the moment of inertia by introducing a small area dA. We are going to discuss the first point. First question to ask, where are you going to estimate the moment of inertia? You are going to estimate it regarding to the x-axis or to the y-axis. From the sketch shown, let x and y two external axes. This is the two external axes, x and y, while the x dash and y dash, these are two axes passing by the CG. If we are going to estimate the moment of inertia, for example, about the x-axis, we need the vertical distance, as we see, from the CG of the D, small infinitesimal area dA. This y, actually, it can be estimated as the sum of two components. The first component is called y1. This y1 is the vertical distance between the CG of dA to the x dash, which is passing by the CG, plus the y bar, which we know before that this is the vertical CG distance from the external chosen xy axes. If we are going to write Ix equal to the integration of dA multiplied by this big distance y squared, it can be then equated to y1 plus y bar squared. And if we are going to estimate for the Iy the moment of inertia about the y-axis, we are going to integrate dA multiplied by the x squared, as we are going to see. In the first case, continuation of the Ix estimation, we need the integration of dA multiplied by y squared, and this y squared can be put as consist of two components, the y1 plus the y bar all squared. We continue Ix equal to the integration of dA, and we are going to get the product of the square. This will be dA multiplied by y1 squared plus 2 multiplied by y1 by y bar plus y bar squared. All will be put inside the bracket and will be multiplied by dA. Then the Ix equal to the integration of dA multiplied by y1 squared plus the integration of dA multiplied by 2y1 multiplied by y bar plus the integration of dA multiplied by y squared bar. This first item, the multiplication of area by the y1 squared, will resemble the moment of inertia about the x dash, which is the axis passing by the CG. That's why we are going to write it as Ix dash plus 2 times this y bar being constant. It will come outside the bracket. We left with dA multiplied by y1. The dA multiplied by y1 is the first moment of area, and since this is the axis about the CG, as we know, the first moment of area is supposed to be 0. That's why all this term will become 0. plus the A y bar squared. So finally, the moment of inertia equal to Ix dash, which is the moment of inertia about the axis passing by the CG, plus the area multiplied by y bar squared. In this regard, sometimes it's easy to estimate the moment of inertia about external axis, and by subtracting the multiplication of the area by y bar squared, we can get the expression for the moment of inertia about the CG. Thanks a lot. We'll continue in the next lecture. Goodbye and see you. Goodbye.